Hello guys, this is Prime Concept. Now we're here to look at a very important concept, which is the concept of electric flux. Now the topic electric flux is something that is sometimes confusing to students. A student asked me one time in my class, he said, what is the difference between electric flux and electric field line? Are they the same? And the answer is no, both of them are actually different, right? So what do we mean by electric flux? I'll be giving you a good explanation on electric flux, trying to use some maybe physical illustrations to help you understand. And the first thing you should understand is that electric flux, the word flux, is actually a Latin word that comes from flow. So electric flux simply means the flow of something, right? Now, the first thing we want to understand is what we mean by a surface area. Now, I believe every student, everybody should know what a surface area is. Now, say I have something like this. So if you observe this, you will notice it has a surface area. And what is the area of this shape? This is a rectangular shape, right? So the surface area is the area for a rectangle. Now, if I bring this, remember we earlier talked about electric field lines. Electric field lines are actually lines. There are lines that are supposed to be coming out from a charge. But you should know that electric field lines cannot be seen with our naked eyes. That is why we said electric field lines are imaginary lines. We just use those lines to indicate the electric field within a particular region, right? So whenever we want to talk about electric field strength, we always try to use lines so that when you see those lines, I mentioned in my earlier videos that if we denote electric field with lines, where you have a lot of lines means you would have stronger field around there. So where you have a widely spaced lines, it means that the field strength in that place will be small. So that is why in order to describe electric field strength, we usually use lines. So that if you see so many lines around a particular place, it means that the electric field will be strong in that place. So if you see few lines separated, right, it means that the electric field would be less strong around that place. So you should take note that electric field is usually denoted with lines, and that is why we call it electric field lines, which is not the same as flux. Now, I earlier showed you a surface. Now, if I denote electric field with lines, say these things I have here now are lines, right? These are lines. So it means that these lines, these sticks you can see here, these lines represent electric field, right? Now, this whole system you can see here, because this is my surface, this white thing is my surface. So what it would mean is that this whole system you can see here is what we call electric flux. That is very simple. So don't try to complicate this issue. Electric flux is simply this system you can see. And what can you observe from this system? Electric flux are the number of electric field lines passing through an area, through a surface perpendicularly. Electric flux are the number of field lines passing through an area perpendicularly. That is to say, the lines must be perpendicular to the surface. And if you watch, even though this is not done to scale, but if you watch, you'll notice that these lines are perpendicular. They are at right angle to this surface. So that's why I said this system in my hand here is what you simply refer to as electric flux. So electric flux is the number of lines, how many lines you have passing through a surface. So what it means is that if you have so many lines, but those lines don't pass through any surface, that is not qualified to be called electric flux. So for it to be flux, flux means outflow of something through a surface, right? I believe this concept is clear. Now, electric flux is actually a scalar quantity. And electric flux is denoted by the symbol phi e. So this symbol here is called phi. That's the Greek name for that symbol. And the reason why we put the subscript e is so that you know that we're talking of electric flux, because we can also have magnetic flux and other kinds of flux. So this is the symbol for electric flux, and you take note that electric flux is a scalar quantity. Now let's look at some of the possibilities and relationship for an electric flux, right? Electric flux is defined as the number of field lines that is passing perpendicularly through a surface. That is to say, electric flux is the product of electric field E and the surface area A. So, and mathematically, electric flux phi E is given as E perpendicular to A. So this is the formula for electric flux. E, which is electric field, perpendicular to the what? Surface. So this is the formula for electric flux. Now we're going to still generalize this formula and come to a better conclusion. But I want you to know that the formula I'm giving you and what we're analyzing currently is electric flux for a uniform electric field. So electric flux for a uniform electric field. Now, when we say uniform electric field, what do we mean by that? It simply means that the electric field lines should be equal and should have same direction. So if you have electric field lines moving in same direction and they are equal in magnitude, it means that the electric field is uniform. So that is what we are considering at this point, electric flux for a uniform electric field. And the relationship is given by phi E equals E times A, right? Now, what is the unit for electric flux? If you check this, we know the unit of E and we know the unit of area. So what it means is that the unit of electric flux is going to be Newton meter square per coulomb. So this is the unit of electric flux, Newton meter square per coulomb. Now, if we consider this case, now there are two things you should understand. If you look at this first diagram, you would notice that this is my surface. I have a surface, right? And then the direction of my surface, that is to say, where this surface is pointing, is indicated by this, which we call area vector. So this is the direction of my surface. Meanwhile, these lines you can see here are what we call the electric field lines. Now, if you notice in this case, the electric field line is passing through this surface at right angle, because this is my electric field and the surface is this, right? So the electric field line is passing through this area, this region at right angle. Now, what does this area vector tell you? This area vector tells you the direction the surface is pointing. Now, this is what I mean by that. I have a surface. This is a surface. Where is this surface pointing? The surface is pointing towards you. So if I want to denote the direction of this surface, I can use something like this marker. So the marker pointing towards you simply tells you that the surface of this book is pointing towards you, right? So this marker that gives us the direction of this surface is what we call area vector. That is what I indicated by this. So this tells us the direction this surface is pointing, right? Now, if I face this like this, this book now is facing up. Now, where is this book facing? The direction can be indicated by this, my marker, telling you that the surface of this book is facing up. So this marker that tells us that it is pointing up, the marker is what we call the area vector. So the area vector gives you the direction of the surface. So please, there are confusing things here that you need to pay close attention to so that you can understand. Now, if you observe this, our electric field is perpendicular to the surface, to this book. It's perpendicular to this surface, but our electric field is parallel to our area vector. And this is our area vector, this is our electric field. If you watch, both of them are moving in the same direction. So it means that in this first case, my electric field is perpendicular to the surface, but parallel to the area vector, right? So if we consider this second case here, case 2, if we consider this second case, you would notice that my surface is pointing up. This tells us that the surface is pointing up, and you can see my electric field moving like this. So you notice that the electric field and the area vector are what? Perpendicular. But the electric field and the surface of this book or of this whatever it is are what? Parallel. That's why you can see the lines like this. So take note of the difference between the surface area and the area vector. The surface area is this thing you can see. The area vector is the line, is the vector that gives you where it is pointing. So these are two separate things, right? Now, if you consider this, you will notice that my area vector and my electric field are at an angle of theta to each other, right? So they are not parallel nor perpendicular in this case, right? Now, we want to generalize the formula for electric flux. Electric flux. So the general formula, so that we can accommodate these three conditions that we can have, because these are the three possibilities you can have, is either that the electric field is perpendicular to the surface, or the electric field is parallel to the surface, which is what you have here, or the electric field is at an angle to the surface. So these are the three conditions. So how do we generalize them? We can generalize using the relationship phi. Is going to now be our general relationship. If you notice, the electric field here is at an angle theta. So it means if I want this electric field to be perpendicular to this surface, I'm going to resolve it. I'm going to resolve it like this, in this direction, right? So, and remember I taught you earlier that whenever you are resolving and you are closing an angle, what do you use? You use cos. So it means if I want this electric field now to become perpendicular to this surface or to become parallel with this area vector, it means I'm going to resolve. So therefore, I can now have that the perpendicular electric field is going to be E cos theta times what now? Our area, or say our area vector. Now, what is theta? Let me still write this. I don't want to rub this diagram yet. So what is, I can now write this as EA cos theta as the formula for my electric flux. Electric flux for a uniform electric field is going to be EA cos theta, so that at any angle you are given, you can always find it. Now, you should know, given from this relationship, that this angle theta is the angle between the area vector and the electric field. This angle theta is not the angle between the electric field and the surface. It is the angle between the area vector and the electric field. That is the angle theta. So we're going to do some deductions from this relationship, right? So I'm going to, I think I should rub one of them. I'm going to rub this. So we're going to do some deductions for this. Now, our first deduction is that you can obtain maximum electric flux. When do you get maximum electric flux? Take note of it. Try to put it down. You can obtain maximum electric flux when the electric field is perpendicular to the surface. Now, if the electric field is perpendicular to the surface, it means that the angle theta between the electric field and the area vector is going to be 0. I will repeat again. We said you can obtain maximum electric flux when the electric field is perpendicular to the surface, like in this case 1. When the electric field, which are these lines, is perpendicular to the surface. Now, if the electric field is perpendicular to the surface, it simply means that the electric field is parallel to the area vector. And remember, theta is the angle between electric field and area vector. So what it simply means is that for maximum flux, theta is going to be what? 0. For maximum flux, theta is going to be what? 0. That is to say, your maximum flux now is going to be, if I come to this formula and I replace theta with 0, I will have cos 0 is 1, so that I will then have that the maximum flux is just the product EA. So this is going to be our maximum flux, just the product EA. The second thing I want you to know is minimum flux. When do you get the smallest or your minimum flux? Your minimum flux is the diagram I just rubbed, so you can go back, rewind the video, and then check the diagram. Now, your minimum flux is obtained when the electric field is parallel to the surface. When the electric field is what? Parallel to the surface. If the electric field is parallel to the surface, it simply means that the electric field is perpendicular to the area vector. It means that the electric field is perpendicular to the area vector. That is to say, you obtain minimum flux when theta is what? 90 degrees. You obtain minimum flux when theta is what? 90 degrees. So when you substitute 90 in this formula, you have cos 90, which is 0. 0 times EA is 0. So it means that the minimum, the lowest flux you can obtain is actually 0 flux. The highest flux you can obtain is what? EA. So if they give you a problem, say find the electric flux through a surface, and they didn't specify the angle at which it is passing through that surface, it means you're required to get the maximum flux, which is EA. So, but whenever they give you a problem, say find electric flux through a surface at an angle, then this is the formula to use. EA cos what? Theta. So what we have done, simply phi equals EA cos theta, is the formula to obtain electric flux for a uniform electric field. Now, what about a non-uniform electric field? It's very simple. So for a non-uniform electric field, remember a non-uniform electric field would simply mean an electric field where the magnitude of the field are not the same and their direction may probably not be the same. That is what we mean by non-uniform electric field, right? Where the field strength at all points are not equal. So for a non-uniform electric field, non-uniform field, for a non-uniform field, the flux through any surface, the electric flux through any surface is going to be the surface integral through E dA. So this is what it's going to be. For a non-uniform electric field, the electric flux through that surface is going to be E dA. Remember, the sign integral simply means summation. So what it means is that if you have a non-uniform electric field and you want to get the total flux through the surface, you have to pick the areas small. You have to divide the area into small portions so that you can analyze the flux through those small areas, and then you sum it up to get the total flux. So you should know that integral sign is what we use in summing up small portions. And that is why the flux for a non-uniform field is the integral, surface integral of E dA. So this is the flux, right? Now, but this is what we'll be using more, because most of what we'll be analyzing for now are going to be uniform electric field. So this one will come later when we want to study the next topic after this, which is Gauss law. Then we'll be looking at this. We'll be starting from this relationship. Now, the next thing we want to do is to take our first example in this video, and then we'll continue in other videos. So we have our problem here on the board, which says a disk. Remember, a disk is a circular surface, right? So that it is not confusing. A disk with radius 0.1. I'll bring out the parameters. So the radius R is 0.1 meter. Is oriented with its normal unit vector. That is to say, what this normal unit vector simply means is what I called area vector, right? With its normal unit vector n at an angle of 30 to a uniform electric field. That is to say, the angle between the area vector and the electric field is 30. So this is our area vector. This is our area vector, which they called normal unit vector n. The angle between it and your uniform electric field is 30 degrees. So this is what we have, right? Now, to a uniform electric field with size. So the size of the electric field, E, is 2 times 10 to the power 3 times 10 to the power 3 in the SI unit, Newton meter square per coulomb. And this is what we have. So we have 3 parts of this question. I will draw up so I can solve them one after the other. So try to get the concept. The first part of the question says, what is the electric flux through the disk under this condition? So when that disk is aligned in this way, what is the electric flux through that disk? So the electric flux through the disk under that condition is what we have as phi E, which is equal to EA cos theta, because theta is this angle between the normal unit vector and the electric field. So we have 2 times 10 to the power 3 times, we need to get our area. We've not gotten our area, so let's start from there. Now, they told us that it's a disk, and remember a disk is circular. So I want to find the area of that disk, which is pi r squared. Remember the radius is in meters, the SI unit. So I have pi, which is 3.142. R squared is 0.1 squared. So if I quickly punch this, I have 0.1 square I have my area is going to be 0.03142 meters squared. So this is my area. So I want to solve the first part, which is phi E, EA cos theta. So my E is 2 times 10 to the power 3. My area is 0.03142 cos the angle is what now? 30 degrees. So if I solve this, I would have, so if I punch this, cos 30 is 0.8660. So I would have 1, 2, 3. So I would have 50, okay? Yeah. So I would have 54.4 Newton meter square per coulomb. So this is what I should have. So this is 1, 2, 3. So this is what I have. Now the second part of the question says, what is the flux through the disk, right? If it turns so that its normal is perpendicular to E. So that is to say, the normal, this area now, is aligned perpendicular to E. So this is what it means. It means that you have your E like this, then you have your normal like this, right? You have your normal like this. So both of them are perpendicular. So what is the angle between them? If they are perpendicular, the angle is what? 90 degrees. So in this, under this condition, when the angle theta is 90 degrees, what do we have there? We have our minimum flux. So under this condition, our flux phi equals EA cos theta is going to be E 2 times 10 raised to the power 3 times A 0.03142 cos 90. Because cos 90 is 0 and you multiply everything by 0, your answer automatically becomes 0. So that is the minimum flux you can have. And the third condition says, what is the flux? What is the flux through the disk if its normal is parallel to E? That is to say, the normal now, under this condition, this is what you now have. The normal, this is our E, and then the normal is now like this. So this is our normal. So they are now parallel. So if they are parallel, simply means that the angle theta is going to be what? You are correct. Thank you. 0 degree. And this is where you have your maximum flux. So your phi E is going to be what now? EA. So E is, okay, EA cos theta. You can simply say EA, but let me just follow this. So E is 2 times 10 to the power 3, 0.03142 cos 0. Cos 0 is what? Cos 0 is 1. So it means you will just be multiplying this. So let me quickly do that. 0.03142 times 2. So this is going to be 1, 2, 3. So this is going to be 62.8 Newton meter square per coulomb. So this is what I would have as a flux. Now I believe this concept is very clear. Do well to watch this video and take notes, right? So that the concept can be clear, very clear to you. But let me still recap. Now, one of the things you should know is that when you are considering the idea of electric flux, you have three things that may tend to be confusing. Electric flux is not the same as electric field lines, right? Electric field lines are just imaginary lines that tells you the direction for which that can give you the direction of electric field. But electric flux are the number of lines that you would have going out through a surface. That is electric flux. Now, another thing you should take note of is that when you're considering the idea of electric flux, you have the surface and then you have the area vector or the unit vector. You have the surface, which is one, and then you have the area vector. So these are two separate things. So the angle theta we always consider is the angle between the area vector and the electric field, not the angle between the surface and the electric field. It is the angle between the area vector or the unit vector and the surface. I believe this is very clear to you. If you have any area of concern here, say it is confusing, do well to leave your complaint on the comment section and I will answer it, I will tackle it. I believe this is clear. Thanks for watching my videos. Do well to subscribe, like and share with your friends so that they can also benefit. Remember, this is Prime Concept. Thank you.